This is lesson 2 of unit 11. In this unit, we'll talk about pressure, the other characteristic that could be measured about gases. The definition of pressure is the force gas particles exert on objects because of their collisions with those objects. So you're thinking about gas particles as tiny little spheres, and if you put those spheres in a closed container, they're going to start striking the walls of that container, and as they do, they're going to impart some force on it. Kind of like if you had a bunch of ping pong balls and you start throwing them against a board. Eventually, those ping pong balls can actually push on the board. And in any sample of gas, there are billions and trillions and quadrillions of gas particles that are all striking against us. And that's what creates the pressure. Specifically, pressure is actually force over surface area. It's the force applied to some sort of area. So the smaller the area, the greater the pressure. You get smaller, smaller, and smaller. You don't have to do too much with this equation, but just understand that it's the particles pushing against the walls. Now, a vacuum is a place where there are no gas particles, and if you don't have any gas particles, there will be no air pressure. It's an environment with no air pressure. Outer space is the closest we get to it naturally. We could create artificial vacuums in the laboratory, but outer space is where there are very little gas particles. Now, pressure usually is measured as atmospheric pressure, and this is the pressure that the Earth's atmosphere exerts on objects, which means this is the pressure due to all the gases in the air that we breathe. Now, the higher up you go, the thinner the air. And so, for example, in Denver, which is a higher elevation than St. Louis, the air is thinner, which means the pressure is lower. So pressure is lower in Denver. St. Louis, we're closer to sea level, or lower, so the pressure is actually higher. The temperature is also lower the higher up you go. But that's here we're looking at pressure. Notice the more particles you have, the higher the pressure. That's kind of the idea. Now, the way pressure was first defined that we know about was using a tube filled with mercury. Now, this is called the Torricelli barometer, named after Mr. Torricelli, who was the first one to do this sort of thing that we're aware of. And it was the first device created to measure pressure. Now, what Torricelli did is he took a tube, a glass tube, and filled it with mercury, and then completely to the top, and then he inverted it inside of a pool, a dish of mercury, and let go. And what happened is the mercury decreased by this amount, creating an absolute vacuum. There are no particles technically in there. Now, the reason why the whole column didn't escape, the rest of the mercury is held up because of the pressure. Atmospheric pressure was pressing against this liquid, forcing it up into the tube. And this is how great the pressure around us is. It can hold up a tube 760 millimeters tall. It does not matter how wide the mouth of the tube is. The tube could have been this wide. It still hold it up. And that's how great the air pressure around us is. So we're going to define air pressure as millimeters of mercury, or we're going to use these units for air pressure, thanks to Mr. Torricelli. There are a lot of air pressure units that are used, and here is the millimeters of mercury, and it was also called Torricelli's, or torr, in honor of Mr. Torricelli. So if 760 millimeters of mercury, or 760 torr, they also equal 1 atmosphere, which is roughly the air that's around us on any normal day. Physicists use this unit called pascals, named after another scientist. And you can also have kilopascals. This is 1,000 pascals. One of the most common units is psi. This is pounds per square inch. Now, to really appreciate the strength of the pressure exerted on us every single day, a square inch is one inch on every side. So on this point, if this were a square inch, there are almost 15 pounds of force being put on it. That's like the weight of a nice and heavy bowling ball. That's quite a bit. And think of any surface and how many square inches that surface has, and you'll get a quick idea that there's an enormous amount of pressure pressing down on any one of us. And this is the reality that we live in. So why don't we do a quick example problem, and this example problem will convert for us from PSI to millimeters of mercury. So we'll convert like we've always done. We'll begin with what is given, along with the units. We'll multiply by a conversion factor. In this case, we're converting from PSI up into millimeters of mercury. We'll need to know the conversion factor. Now, if you take a look at the previous slide, the conversion factor is 760 millimeters of mercury equal 14.7 psi. This is our conversion factor. So 14.7 goes into the psi, 760 into millimeters of mercury. What we end up doing is multiplying 18.9 by 760 and dividing that by 14.7. And that's how we get 977 millimeters of mercury. So be able to use these conversion factors. That shouldn't be too bad. We've done this plenty of times. But just in case, go ahead and practice on your own. Why don't you try this one here? Convert from 93,200 pascals to torrs. And finally, we're going to say there's a special set of conditions called STP, and this stands for standard temperature and pressure, that chemists or other scientists have agreed upon when reporting about gases. So these are the temperature and the pressure under which many gases are measured, many gases are reported, because it turns out if you measure something about a gas, say the density of a gas, if you increase the temperature, the density changes. If you decrease the pressure, the density changes. So we have to come up with a set of standard conditions under which we'll talk about, under which we'll measure our properties. Okay, so this completes for us Unit 11, notes for chapter, or notes 2.